Hello everyone, I hope I'm online. Just let me cross check in the chats. Okay. So today we'll talk about the image formation in microscopes, the basics behind that. Am I online? So today we'll talk about the image formation. Yeah, so the voice is clear, everything is good. So who is online? Just say hello, such that I get to know who is online. Yep, so today we'll talk about image formation in microscopes, which is an important topic in any MSc level entrance examination or anyway for research. You need to know this. Okay guys? Okay, great. So I see 5 people are watching at least. So hello Pritam, hello Devashmita, Vaishnavi, everybody. So we'll talk about how image formation in microscope takes place. Okay? So everybody is ready? Shall I start? Vaishnavi, Pritam, Devashmita, everybody is ready, right? So all about this microscope image formation was discovered by Ernst Abbe and then modified by many other people. Okay? So we'll also look at what type of questions are asked in GATB, whether we can answer them or not after this class. So stay tuned for this, only 30 minutes, and it would give you a lot of benefit, okay? So this is how a microscope working principle would look like. So here would you have objective. So you have two convex lens setup. One which is closer to the object is known as objective. One which is closer to your eye is basically eyepiece. And other than that, there is just a tube, okay? So it's basically a tube, right? Now here, this particular object is placed within the focal length of a objective lens. So you can see there is an image formation here, right? Such that this particular image works like an object for the second lens. And this particular second virtual object is basically giving rise to another image. And this particular image, you can see it is quite magnified and it is also virtual, right? It is magnified and virtual, right? So basically this is your image plane, right? This was the object plane, this is your image plane, which is infinity. So now your eyes are able to capture that. Either your eye captured that or your microscope camera captures that. So this is the overall framework of compound microscope that you have learned in class 12. So no doubting that part. But let me give you a little bit more overview that how exactly images are formed. So accordingly to Abbe's theory, what are microscope images? Microscope images are nothing but diffraction pattern. So each of these microscope images are composed of several diffraction limited spots, okay? And all of these spots would have different intensity. Different intensity would give you different feature, right? One particular image of a cell might have some, let's say, bright feature, dim feature, etc. But together these features would make sense, give you a contour or give you an overall shape, right? And the final image is basically overlap of all of these features, okay? So that is your final image. So if we try to understand that this is your object which is placed on your slide in this location. So maybe this is your cell and light passed through this cell, and through this objective it is focused towards the back focal length of the objective. So this is known as back focal length of the objective, okay? So this is the back focal length of the objective, back focus of the objective, right? So this is the front focus and this is the back focus. So in the back focus, what you can see, this point is now not appearing as a point. So it's a point source, right? So we started with a point source, but now this point is not behaving like a point. This point has spread a little bit. So this is due to a little bit of aberration in your microscope optics system. But overall, it's like a point, right? So this function, which basically defines how much a point would be spread, It's known as point spread function. It also tells you how accurate your microscope is, whether it is free from any kind of optical aberration or anything, right? And you would definitely like a microscope which would not have any optical aberration. By the way, all of these cartoons and everything are taken from Nikon Microscopy U website. That's a brilliant website for learning microscopy if you really want to learn microscopy. But anyway, these are not my images. So here you can see these intensity spots. If you plot this in 3D, this would look like this, where here this is the central maxima, followed by other maximas, different order maximas, right? So this is how the intensity distribution is created. So here 84% of the intensity is like here. So each point would spread a little bit, okay? Lesser the spread, greater would be the image quality, because we want to see a point and point's image should be a point, but it would be a little bit spread due to the optical aberrations. So we understood that part, right? Everybody clear? Everybody, is this clear? Whoever is listening, say something such that I know. Clear, guys? Clear, right? सब लोग कहाँ गए? क्या हो गया? What happened, guys? Okay, ठीक है. So next what happens? So that was the most simplest example. Now let's take a complex object. It's not a point object right now. Our object is again a geometric pattern in this case. So in this case, you see the geometric pattern. This pattern is basically some bars. So this is called a diffraction grating. Okay, this is called a diffraction grating, right? So this would, in 2D, this would look like this, right? There would be black patterns, and through which here the light can pass. Light can pass through here, right? Yeah. So obviously, what you can see, the diffraction grating is here. The specimen is a grated, a geometric specimen. Now it would progress in the front, and ultimately it would be focused by the objective lens. Where it would be focused? By the objective lens. Objective lens is basically a convex lens, so it would converge the light into the objective back focal plane. Okay, so this is the rear focal plane or back focal plane. And the image, the diffraction image, so this is not a real image, this is a diffraction image. And the diffraction image should exactly look like this. You see? This is the diffraction image. So basically all of our microscopy image are composite of all of these patterns. Let me give you an example. So previously we looked at only one particular image or one particular object like this. So point spread function correspond to one particular point object. Now you see there are intensity distribution of so many points, and this totally makes up an object. Okay, this totally makes up an object. This might be localization of some protein. Imagine this might be some localization of some protein. So this is basically your microscopic object. Microscope image. So whatever you see as an image in the microscope is actually this. At a bare minimum, they are nothing but diffraction patterns. You must be amused to know, right? Okay, so let us talk about why we are talking this. Do we really need to learn from these details and what is important? So I think it is important to learn, because look at this question, which is from JNU 2018. This question says the resolving power of a microscope can be increased by increasing the diameter of the eyepiece, decreasing the diameter of eyepiece, increasing the diameter of objective, decreasing the diameter of objective. So resolving power, how it is related to diameter, how it is related to the diameter of lens. So any idea which would be the correct option? Any idea which would be the correct option, guys? Come on, write it in the comments. Take your time, read again. The resolving power of a microscope can be increased by increasing the diameter of the eyepiece, decreasing the diameter of the eyepiece, increasing the diameter of objective, or decreasing the diameter of objective. Come on guys, tell me, what would be the answer? This is a JNU CEB question. So this kind of questions are expected in GATB. So if you are not familiar with this question and if you are not able to understand how to proceed in these kind of questions, so then this video is for you. And you need to stay tuned till the end, because we were going to practice few questions which are related to these kind of topics and concept. So कोई नहीं कर पाया इस question को? कोई नहीं कर पाया क्या? What happened guys? Or this is just a server lag? What is happening? I don't know. Is anybody answering? Nobody is answering guys. Where are you guys? So before solving this question, I would move on and learn about the concept. Then we come back and solve this question, okay? The correct answer would be option C, which means increasing the diameter of objective. So somehow it says that resolving power is kind of proportional to the diameter of objective. Why? Why is so? So let's see that. So guys, let me tell you, what happens if your objective diameter is more? You would collect more and more diffraction patterns. So obviously you see in D, in terms of image formation, this is the best scenario, because you have so many order of diffraction images. So you have 0th order, 1st order, 2nd order, 3rd order, 4th order. At least 4 diffraction order is collected. So one particular thing, remember this thing, greater the diffraction order, is collected, better would be the resolution. So look at this particular A and B. So here you can see there is 0th order. So diffraction means what? Bending of light. Question is how much light is able to be collected by these objective lenses. So here you can see not too much order of light, only 3 orders of light are captured here. But see in this second scenario, there is more light which is captured, right? Due to the change in something. So there is more light which is captured, okay? And that is why you get more diffraction patterns. So at least what we learned so far, that every microscope image is nothing but a diffraction pattern. It's an interference phenomena of this diffraction pattern. That's the exact quote unquote thing that Abbe mentioned. Interference phenomena of a diffraction due to diffraction, okay, due to the diffraction lights. Now you understand this part, right? So this would be the worst image because it has only 1 order of diffraction light. So 1 order of diffraction light is not able to create interference. Now at least 2 diffraction orders are required. At least 2 diffraction orders are required to form images. So now everybody